but I need to go over it because it is part of math, high school math. It is not included even in university courses, but it is a key for cornerstone for all things that we did. And maybe you already know the answer. So let me challenge you with a little question. If I do have a progression, 1 plus x squared plus x cubed plus xn plus x to power infinity, and x is between 0 and 1, what would be the result? Like if everyone knows the answer and knows where it comes from, then we do not need to waste about half an hour of time. Okay, let me make it more spectacular, but I will still need to do derivations. So I'm drawing a square with each side equals 1. Okay, let's consider as an example x equals 1/2. The area equals 1/2 is a half of this square, right? So this is area equals 1. Here's area is 1/2. Benjamin, would you like to come and help me? I'll tell you what to do. So can you, like, if you have 1/2, 1/2 to the second power, which is 1/4, can you graphically put?
Does that be like 1/4?
Yeah, 1/4. Maybe closer to here. It will be 1/8. 1/4 will be 1/4 of the area. Like a square with 1/2 of each side.
Okay.
Okay. So it will be about 1/16. If you have like let me mark. So this is 1/2 in length. This is also 1/2 in length.
So
okay. Okay, and just put 1/4 inside. 1/4. Okay, yeah, thank you. Rebecca, would you like to help? So x to like 1/2 to the third power will be 1/8, right? Can you add a geometrical figure that will be, you have area 1/8? Down, down, down. It will be not square, but yes, and put 1/8 inside. Yeah, thank you very much. Max, would you like to help? So x to the power 4 will be 1/2 to the fourth will be like 1/16. Okay. Yep, thank you. Sorry, would you like to come and help? So the next x to the power 5 will be 1 divided by 32, and you add a figure. Yes, put 1/32. Okay, thank you. Adam, would you like to help? So do you see a trend? You may not, instead of drawing, just tell how do you see what happens. Okay, and if you continue, and if you do like another, and what will be the final area of the sum, adding together all figures? Everyone agrees with Adam? Okay, yeah, thank you. So for 1/2 it will be 2. Now we need to obtain 2 out of this number. What about 1 divide 1 minus 1/2. So it is 1 divided by 1/2 equals 2. Okay, so the generic formula will be 1 divided by 1 minus x. Convincing? It's no way a mathematically rigorous derivation, but at least you get an idea. So how would we call this progression and its summation? Now we are preparing ourselves to serve as high school teachers.
Geometric progression.
Yes, exactly. So there is arithmetic where it gets by the same offset each term, and now it's several times bigger. X time bigger or x time smaller each set. So summation of geometric progression. So I'm going to erase it and use the space for a little bit more rigorous derivation to be, but with this or a little higher level of rigor, it is a cornerstone for blackbody radiation and for statistical thermodynamics, and also for field theory in physics that is used to design like nuclear reactors. So it's very powerful, like simple but powerful trick. So summation of n terms. Here is my little cheat sheet. From 1 to n, common term, then q I minus 2. So we need to design an equation to prove an equation that will be something like 1 minus q for this summation, and some additional terms because it is not infinite but finite. The plan of a proof is as follows, or derivation. One takes first term away, then has reduced part of summation here, puts common factor away, and then one adds and subtracts next term, like term of n plus 1. And then one identifies that this part in the bracket will be equal to, well, plus next term will be the same term at the beginning. And then one forms, like puts it outside of the bracket and finds the answer. So let's try to do it. So for I equals 1, should be not 2, should be 1. For I equals 1, we'll have q to the power 0. So it will be b times q to the power 0, and then the rest of summation, we go from I equals 2 to n, b q I minus 1. I can put u outside of brackets, and then as a price for it, I will put number 2 here. Now the next term will be for I equals n, and we need the I equals n plus 1, and then I minus 2 will be equals n minus 1. So I'll put q to the power n minus 1, and then subtract q n minus 1. So it is a legitimate mathematical operation. I add and subtract the same thing. Okay. Now, if I combine these two things together, I'll have q outside, summation from I equals 2 to n plus 1, b q I minus 2. So, but I do start counting from 2. When I equals 2, power equals 0, right? So it will be 0th order term, which doesn't have q, it will be only 1, right? So I can rename it as like I prime equals I minus 1. And then after this trick, so after this trick, I will get summation from I prime equal, starting from 1, ending at n, because I subtract 1, times b times q I prime minus 1. Look there, it is exactly the same thing. So this term can be renamed as S sub n. Q times F sub n. Here it will be just a free term b, S sub n, and here we have minus q minus b times q to the power n. Right? I didn't lie yet. And now let's put S sub n to the left. So S sub n minus q times S sub n equals b minus b q to the power n. So here I can put S sub n outside of the brackets. 1 minus q equals b minus bqn. And then I can solve for S sub n, b minus b q sub to the power n, 1 minus q. So if we set n equals infinity, then it will be just b divided by 1 minus q. If b equals 1, then it will be just 1 divided by 1 minus q. Right? So we do have a summation of geometric progression. Thank you for your patience. Do I have a permission to erase this boring stuff? Okay. So now you can teach math at high school with confidence. Although no one of us has it as a life goal. Do you agree? So if you need expectation value of energy, we just find we need to know wave function, and then we find the average. So this is quantum approach. if we do like statistical thermodynamics approach, we will change the paradigm. Well, one can make another line for discrete representation in the eigenstates. So if the wave function is represented discretely, then one can find it in the matrix form, right? And if the Hamiltonian is diagonal, then H equals E n delta Mn, then a favorite object of Adam and myself, rabbit, and summation annihilate each other. And then we have summation over only one C sub n absolute value squared E sub n. And then C sub n absolute value squared is probability that quantum level number n is occupied. So if you have harmonic oscillator, we may have a superposition of so many percent, like 50% in the ground state, 30% in the first, like 10 in the next, 5 in the next, right? One can have distribution. If we play a game of quantum mechanics, then the probability to find system at each quantum level is defined by initial conditions. And since in silly quantum mechanics, everything is considered isolated, the distribution doesn't change over time. But if we cross the borders, if we depart silly quantum mechanics and go to advanced quantum mechanics and statistical thermodynamics, we violate the forbid for isolation. Everything becomes coupled to each other, right? So each quantum system exchanges energy amplitude with environment, with surrounding systems. Because as chemists, you know that there are no isolated molecules. It's in a solvent, on a substrate, right? On a hot plate. So when we depart from quantum to statistical, then this probability is not given once and forever at the beginning, but for systems in equilibrium, it comes as the energy of state divided by Boltzmann constant, right? Here you can stop me and tell I don't believe you, prove it, but I don't know how. It's just something that we all believe. And when we hear it for the first time, again, I think it is, sometimes this idea is introduced not even before the freshman time in high school. The argument to believe Boltzmann distribution is describing a lazy person who doesn't clean the room with shelves, with dusty shelves, and look at your experience, which shelf is more dusty, lower to the ground or higher to the ceiling. And people in the audience should have this experience and know that there are more dust in the lower shelf. So if we accept this thing, this is the main practical step. The rest is the math. Philosophically, how to justify it is like a lot of thinking and a lot of discussion in the community. But we do have a goal to describe emission light from black body. There is a thing that I do not know how to address. So, black body is assumed in modern science as a box of mirrors with captured photon modes, and all derivations will deal with harmonic oscillators for each photon mode and then looking for its quantum state if it is not isolated. But from the simple human experience, we know that what is emitting light is material objects, like filament of incandescent lamp or collection of gases in the gravitational trap on sun. And interestingly is that it absorbed and remits light so many times that although hydrogen and helium have linear spectrum of absorption and emission, right? The sun itself gives us continuous spectrum. So maybe highly excited atom has very smaller transitions, right? And then by contributing all possible transitions, it gives us the continuous spectrum. Okay, but now the strategy is as follows. We believe that any black body is a box of size L with mirrors, and inside each mirror there are standing waves of electromagnetic radiation. So this standing waves of electromagnetic radiation, it's like electric field, is has this spatial distribution and it has the time distribution. So in time it oscillates. And the way of this, how it goes in time, can be considered as quantum harmonic oscillator. So if one extracts the energy of individual mode of a given frequency, of a given wavelength, then the amplitude, this electric field amplitude, will have distribution over positive and negative elongations, and it will obey the same Hamiltonian, same math as harmonic oscillators, which in chemistry apply to small elongations of the intermolecular bond, right? So box with mirrors, with a lot of oscillators. Oscillators are electric field, and each oscillator is quantized. So the derivation of the shape of the emission is composed of two parts, which are, I wouldn't say which one is more important, but one part deals with isolated mode, not isolated, selected mode, and dealing with quantum state, quantum statistical state mode in the equilibrium with the rest, and finding what's the average energy of a given mode. And second part is making summation over all possible modes. Summation over all possible modes is treated in the same way as one treats particle in the three-dimensional box in quantum mechanics, and in the same way as one derives LDA functional in density functional theory, just assuming box with different quantum numbers. But I will postpone this part to the next meeting because it can be a little boring and not pleasantly accepted by the audience, but it is not a dramatically new science. The key part is to get our minds around combining quantized quantum levels and Boltzmann distribution. This comes to the second part of the first part, like second part of my portion of this course. So when we depart from quantum and go to statistical, so how the quantum levels are being populated if they are in the equilibrium. And they are populated just by Boltzmann distribution, but we need to learn simple tricks, simple approaches, how to get two observables. And at least in the example that we are considering today and on Wednesday, the way how to get the observable will be related to this geometric progression summation. Okay. So suppose we do have only one mode, frequency lambda, wavelength lambda, frequency omega, and then the when we were playing in game of ladder operators, you were telling that Hamiltonian is h bar omega dagger a plus 1/2, right? You remember it, right? If we know that the system is loosely coupled or not coupled to anything, one can tell that the Hamiltonian is h bar omega diagonal projector times n plus 1/2. Or simply one can tell that energy level number n is h bar omega n plus 1/2. So they are offset by h bar omega. We will make our life, our mathematical life in the remaining whatever time in this meeting, much less problematic and much more pleasant if we shift the origin. Right now, the origin is set up to the minimum of parabola, right? But you know, in math, you can add and subtract things, change origin, and no one will punish you for this. So if you change the origin to the energy of ground state, then under this trick, you can tell energy level number n will be h bar omega n. So if you are not looking for time-resolved quantum interference, this is very, you see, it's just a couple of symbols less, but it simplifies derivations substantially. Okay. So the idea is that just going to math is dangerous in the following sense, that we will make an effort, we will win over these mathematical challenges, and then we will have empty memories, no positive information about background ideas. So it's better to make an attempt to return to what we are doing and why. So the idea is as follows. When we have a collection of multiple oscillators, and each of which is following Boltzmann distribution, we will see that oscillators with lower energies, lower frequencies, will have more and more levels populated, will be more excited, right? If temperature is fixed. Oscillators with higher frequency will be less excited, right? Because thermal activation is not sufficient to promote those oscillators into higher excitations. Make sense? And from this point of view, you will see the idea that the higher frequency oscillators contribute less to emission than lower energy oscillators. So if temperature is finite, it could be insufficient to populate oscillators of like blue, UV, purple, and therefore their contribution to emission will be diminished. While those with lower infrared contributions, they will be overpopulated and they will contribute a lot of quanta and will give us the signal in the emission. So this will deal with a factor of considering individual oscillator, and we will get through it. So we just need math that help us to address this fact that the higher frequency, less quantum states are populated. Nothing else, but we just need to suffer math for it. Second factor will provide us density of states, where the amount of oscillators does depend on frequency. The smaller the frequencies, the less smaller amount of oscillators is available. Well, if you go to higher frequency, we will prove it on Wednesday. It's not complicated. It's not a new science. It's something like regular and basic. But if you go to higher frequencies, there are more and more oscillators available. So when we go to lower frequency, degeneracy is less. Less oscillators are available, and this factor will compete with our primary consideration. Like there are so many activated, any low frequency oscillators are activated by temperature, but degeneracies, the amount of low frequency oscillators is less. As we go to increasing energy of oscillator, it will become less and less populated, but more and more degenerate. And there are two trends. One trend that higher energy gives less contribution, another that there are more higher energy oscillators. And as we go forward to higher and higher energy, first we will get an increase in intensity because the degeneracy changes, but then after some threshold, no matter what is degeneracy, if they are not populated, if oscillators after some threshold are in ground state, they just do not contribute to emission. Therefore, there will be a shape with a maximum, with a peak. Make sense? Okay. There will be nothing else more in today and Wednesday, but we need to go over the equations. So for selected oscillator, I just rewrite this one. Summation of n, probability n, energy n. And then the probability is e to the power minus energy n over kT times En. This equation is wrong. It's correct in principle, in idea, but for any practical calculation is wrong. And I know that Patricia has her favorite word related to quantum mechanics that will give answer why this equation is wrong. Patricia, would you like to switch on microphone and tell?
Okay, sorry, I didn't get the question.
When we find expectation values, what should we do to make it correct?
You normalize.
Normalized, yes, thank you, Patricia. So it should be normalized. So if we repeat this equation without energy, if you just do summation of these probabilities to infinity, it should be 1, right? Or if you want to have the equation absolutely correct, we do need E equals summation n p n e n divided by summation n p n. So anyone has objections, or it seems like kindergarten level clear. Natural. Okay. So statistical mechanics sounds, for some people, sounds scary and unnatural, but it has nothing in addition to this simple equation. Everything is related only to this equation. But people who practice it want to sound smart and respected, and they design a special language. So the summation of these probabilities that come into denominator is typically denoted by letter Z, sometimes W, and it is called statistical sum. Statistical sum, or some people call it partition function. Partition function. Let me do one more mathematical experiment. So if I literally plug in the Boltzmann constant, En, there is another. So they just design their own world and do simple things in a complicated way. So I think we all do not mind Boltzmann constant. We don't mind temperature. But some people hate them, and they want to rename them to get simpler notation. Adam smiling, it looks like you know how to replace it. Like, huh?
Just call it energy.
You can call it energy, or so energy divided by this thermal energy, right? But something in the denominator is not super comfortable, because we want to make main mathematical feature of exponential that derivative and integral of exponential is exponential. But one needs to have things in the numerator, not in the denominator. So one just calls 1 over Boltzmann as a new variable. Okay, so it's only a matter of comfort, but without this declaration, looking at any materials related to statistical mechanics immediately drives us from the comfort zone, because they have different notations. So they have this partition function and they have inverse temperature as beta. But it is language of this area of science. So minus beta E sub n times E sub n. Now there is a little justification why this trick is introduced. So mathematical experiment. What should we do to the function minus beta E sub n to obtain E sub n? And natural log, what else? How to extract thing? Yes, exactly. So if we write it here as summation of n d beta E minus beta E sub n, it will be, by taking derivative, when is minus sign, right? One will get the same expression backwards. So by taking derivative over beta, one will get E sub n, and then the function is itself is reproduced. Okay. So now I'm going to erase this because it's equal to what it was there. A little more trick. summation and derivative are interchangeable because there are no operators or wave functions between them. So one can put minus d beta summation e to the power minus beta e sub n, which just p sub n. Do we see a definition of this black box anywhere else on the board? So it's partition function, right? So we do have expectation value of a variable is minus d beta of partition function divided by partition function. See, it looks, on one hand, it's very simple, on another, it looks crazy because it is a new notation. And it's very different from how we write down equations for quantum mechanics. Okay. So this is something that you may record and benefit towards your future career. This is something universal that will be used again and again. And now we can return back to the example that we are processing. So I'm going to plug in things related to a single harmonic oscillator, practice the summation of geometrical summation, and then we will be done for the day. I just don't want to erase and try to focus on the remaining part of the board. Okay. So partition function for e to the power minus h bar omega n either divided by kt, or we can do as a true statistical mechanics people, right? Use beta. Okay. So partition function for one harmonic oscillator, and we do, this is infinite series summation. But can we simplify it based on our today's exercises? So we can consider it as e to the power minus beta h bar omega to the power n, right? So if in case are there any situations when this exponential will be bigger than 1? Probably for very high frequencies and very low temperatures, but generally it is for low frequency and high temperature, it will be a small number. And even if we fail this limit, we can practice it. Just take it as q or x, and then just get the knowledge from our high school geometrical progression. So the result will be 1 minus q. So 1 divided by 1 minus E minus beta H bar omega. So the summation of many terms is less comfortable. And here is mathematical function that we can draw, right? As function of temperature or as function of frequency. Now let's practice. So we are done with denominator. So at this point, it's time to practice the nominator. So we do minus d beta of z minus d beta of 1 over 1 minus E minus beta H bar omega. Now I can step off and let you do this derivative, or I can do it myself, but it shouldn't be a big challenge, right? So we can treat this one as 1 minus this stuff to the power of minus 1, right? Right? So what is the derivative? What does derivative makes to the power? X square prime equals 2x to the power 1. So the power decreases by 1, correct? So we are getting minus 1 minus E minus beta H bar omega to the power minus 2. And we should get this factor minus 1 up front. Correct? Catch me if you can for credit. But now it is not done story. We need, and after this we need to take derivative of the content of this shell, of this what was in the bracket. So d beta of 1 minus E minus beta H bar omega. So derivative of 1 is 0, and then we need to apply derivative to exponential. It's minus 1, I think it will be plus 1 minus E minus beta H bar omega to the power minus 2. And then derivative of the exponential will be over beta will be minus H bar omega. Exponential stays itself, beta H bar omega, and we have another minus here. So there were 2 minuses here that canceled, and here there are 2 another minuses that cancel into plus. So we are getting H bar omega times E minus beta H bar omega divided by 1 minus E minus beta H bar omega squared. And this is our minus d beta of z. Make sense? If you find any errors, it will be generously credited. And now we just need to divide numerator by denominator. So average energy of oscillator minus d beta z divided by z. So first we do the numerator, which is H bar omega E minus beta H bar omega divided by 1 minus E minus beta H bar omega squared. And then we need to divide by the denominator here, which means we just multiply by this stuff. You're following? 1 minus E minus beta H bar omega. Then we can cancel this one and power 2. H bar omega E minus H beta H bar omega divided by 1 minus E minus beta H bar omega. We are almost there. One can divide left and right by the top and bottom, numerator and denominator, by the same factor. So if we divide numerator by this one and divide denominator by this one, then we'll get 1 here, 1 there, and here we will have the same expression with a minus flipped to plus. H bar omega E to the power plus beta H bar omega minus 1. So how, and this is average energy. So if temperature equals 0, beta equals infinity, we will have H bar divided by infinity, right? Infinity minus 1 will be still infinity. So energy equals infinity, which means in the far infrared or radio frequency, we will have overpopulated oscillators that are ready to emit vividly, right? If you have,
if T is 0, shouldn't the average energy also be 0? Because you divide.
yes, 0, correct. Max plus 1. Yes, 0. So 0 energy, everything will be in ground state, not emitting. Now for infinite temperature, beta equals 0. E to the power 0 will be 1. 1 minus 1 will be infinity. And then H bar divided by 0 will be infinity. So energy will be infinity. So for infinite temperature, they will be, any oscillator will be like vividly emitting. For 0 temperatures, they will be in the ground state. And in the middle, there will be a progression that we can just draw this function. So the equation from here will be multiplied by density of states, which will be Ts of frequency will be proportional to omega squared, and the final answer will be looking like omega to the third divided by this E beta H bar omega minus 1, and this function is raising, this is decreasing, and it will give the peak. But we will need to do it carefully and analyze over and over again. There is a interesting observation or interesting historic fact. So the idea of quantum levels being occupied less and less in equilibrium was not very usual. The fact that there are discrete energy levels was not usual. And the fact that the energy depends on frequency times Planck constant, it was not always with us. It was designed. So this story about emission of black body was a reason to design Planck constant. And in fact, the numerical value of Planck constant was designed before quantum theory, before Bohr model, before considerations about angular momentum. Planck constant was introduced as a fitting parameter for this equation to match solar radiation. So it is a history of how Planck constant was designed and why Planck got Nobel Prize, and why we call the constant after him. It's all of my plans for today. There is no homework for Wednesday, but on Wednesday I'll offer a little MATLAB exercise of feeding the experimental data to equation and doing some considerations as a homework for the next week. So I'll be very happy to just address any questions here, but if no, everyone is welcome to disconnect and depart. Thank you for assistance with.
Yeah. So, temperature. Those, every transition on the middle of the discrete energy levels becomes available. Okay. Like it's like keys on a piano.
Yes, it's like playing a chord of all keys simultaneously.